So today is the third last lecture of this semester. Okay, including today's lecture, we still have 3 lectures. Okay, pretty much like for this month. Okay, this month. No. This month and the first week of next month. Yeah. So, okay. So let's. We finished last time we finished the dynamic programming, and we talked about greedy algorithm, and we talked about Prim's algorithm. Okay, Prim's, how to use Prim's algorithm to find minimum spanning tree. From a connected graph. One moment. But we haven't finished the analysis of the algorithm. We talked about the correctness already. Okay. So we talked about the proof. Okay. But yeah. We talk about this algorithm, and I show you with an example, a running example, and then here is here's analysis of the algorithm. It's actually very, very straightforward. Okay, you see here is the initialization. Okay. This initialization, because obviously you need to push all the vertices to the queue, priority queue, with the key infinite. Okay, and this takes proportional to the number of vertices, right? And so this is the theta v, and while Q is not empty, every time you try to obtain one node from this priority queue, okay, which store like the shortest link, okay, from the current set S to the node outside of S, and obviously after you pick such a node, okay, with the smallest weight h that connected outside of the set S, you will add that node to the set S. Okay, so here, okay, every time you run this loop, okay, you decrease the number of nodes in the queue. So you run this loop, while loop, number of vertices time, okay? And then, you need to, you get this one. This one is log n, okay, pretty much. But how about this? For each v in adjacent, you do blah, 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 blah. So here it is proportional to the degree of u. In the worst case scenario, you do need to change the key value for all the neighbors, use neighbors. okay, where U is the one that you selected, okay. So you need to change the key for all its neighbors. So this for loop is proportional to the degree of U. But think about this, okay? If you count this one like separately, it is expensive. But we know, like at the beginning of this chapter, we talk about a handshaking theorem, right? So the total number of degree, okay, is 2 times number of ages. So, in other words, okay, this statement, okay, according to the handshaking lemma, okay, this statement totally would be wrong, well, at most theta 2e, 2 times e times. I mean, it will be bounded by this value. I mean, it will be much smaller because, like, it's not that you have to decrease the key for every neighbor. You only need to do that when this condition is met. Okay, so it's not like for every neighbor, but this is the worst case scenario. Okay, so having said that, okay, it's going to be, because remember I told you, here you need to pay something to extract the mean from your priority queue, which is usually a tree. And here, I mean, as I said, the total number of time to run this statement is theta e. So theta e times, for this one, it's also decreased key. This is extract mean. This is decreased key. So, but we're talking about priority queue, right? So this is like what we have. But for priority queue, there are different ways to implement the priority queue. Okay. The easiest way to implement priority queue is obviously using the array. If you use the array, every time you obtain the mean, okay, you need to, rearrange the whole thing so it is linear. Okay. And but to decrease the key, it could be fast. Okay, it takes constant time. So the total would be, theta v times v. So this one is v squared, and this is e times a constant. But this one, because this order, the order of the first term is going to dominate the whole thing. So it's going to be big O v squared. Okay, but in previous chapters, we also learned you can use heap to implement priority queue. If you use binary heap to implement priority queue, then extract mean is log v. Remember, like we talked about heap sort, right? So the heap sort, I mean, in the heap sort chapter, we talk about heap. Heap is essentially a priority queue. It could be used for priority queue. So it is like very efficient in terms of like extract mean, okay? And for decreased key, okay, it is also log, and it is worse than array, but at least like it improves both operations. Okay, at least both operations will be log v. So if you plug in these two in this formula, you will see like the the time complexity for Prim's algorithm becomes big O E log V. Most of the textbook ends here, okay, ends here. Okay, but some only few textbooks go one step further to talk about Fibonacci heap. But for Fibonacci heap, okay, the amortized cost for extract min will be log V, and for decreased key, okay, the amortized cost will be constant. Okay, so if you use this one, okay, it's going to be this one. Okay, so well, is there any like a big difference? Actually, not that much. Okay, but yes, like because E when your graph is dense graph, this one is cheaper. Okay, because when a graph is dense graph, E is proportional to the V squared. It becomes V squared log V, and this one becomes V squared plus V log V. So you can see there's a difference in terms of order. But when your graph is not so dense, say it's a sparse graph, then E is proportional to the number of vertices. In that case, these two are similar. Okay, but anyway, I would not talk about Fibonacci heap because we really don't have time now. Okay, so you know, as long as you understand the top two, I think that's good enough. Okay, that's good enough, especially the binary heap. Okay. As for Fibonacci heap, if you want to learn more, after we talk about amortized analysis already, right? So you can, you know, study by yourself and see like how it can improve the time complexity here. Okay. So to end the discussion of this chapter, okay, first we talk about one greedy algorithm, which is Prim's algorithm. There's another algorithm, okay, which is also very famous to deal with minimum spanning tree, okay, which is called Kruskal algorithm, okay. But it utilized the disjoint set data structure, which again we did not discuss in this class because of the time constraint. Okay, I have to skip that. But the running time for the Kruskal algorithm will be E log V. So you can see that E log V is as good as binary heap, right? So usually, okay, if I have time, I will cover Kruskal, but we only have including today's lecture, we only have 3 lectures. So I prefer to cover shortest path, okay, and then the min-max flow, and then NP hard. Okay, it's already a lot of content. I hope I can do it, but if I cannot do it, I mean, I will not try to speed up my lecture, you know, because I don't want you guys to, you know, to have hard time understanding the material. Okay, and the best MST algorithm to this date will be this one, Karger, Klein, and Tarjan, which was proposed in 1993. It's a randomized algorithm, and the expected time complexity will be big O V plus E. That's pretty good, okay, compared with the previous ones. But you can see that the best they can do is the expected time complexity, not the worst case time complexity. Okay? So that's it for this chapter. And which means like this is also like end of the second chapter. So as before, I will assign one homework assignment, okay? But I think I will be able to finish the at least one shortest path. There are actually 3 shortest paths, like chapters or lectures to cover. So as you can see from the title of this lecture, this is shortest path 1. We have 3 lectures for shortest path. Okay, the first one is for mostly Dijkstra. The second one is for Billman-Ford. The third one is like what's the name? It's all paths, shortest paths. Okay, so I think that's a Freud algorithm. But anyway, okay, so this is also one of the most famous graph algorithms. Okay, or put it another way, one of the most famous graph problems out there. Okay, so what is shortest path problem? Okay, here, given a directed graph, I mean, it could be directed graph, it could be undirected graph, okay, but the problem is essentially the same. Okay, obviously, directed graph is a little bit more difficult than undirected graph, but anyway, it's similar. Okay, so you are given this graph, okay, with age weight function. Okay, so you know like each age is associated with a weight. Okay, and the weight of path P, okay, from V1 to V2 to blah, 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 to Vk, okay, assuming we have like k nodes on this path. So if you have k nodes on this path, okay, we define the weight of paths to be Wp, okay, so it's going to be summation of the weight of all the ages in this path. And obviously in this path, because we have n nodes, so totally we have n minus 1 ages, right? Okay, 质数问题嘛，对不对？ So this should be very straightforward. Okay? So one example would be like this. okay, in this path, we have V1 to V2 to V3 to V4, and finally V5. And the age between V1 to V2, the weight is 4. The weight for the age from V2 to V3 is -2. The weight for age between V3 to V4 is -5. And the weight for age from V4 to V5 is 1. So the total weight, okay, for all these ages, which is the weight of the path, will be -2. Okay, it's 4 plus -2 plus -5 plus 1. Okay, it's very, very easy. So once we define the weight of a path, okay, now, okay, we can define the shortest path. Okay, a shortest path, okay, from U to V, okay, from one node to another, okay, is a path of minimum weight from U to V. So you may have many, many different paths from U to V, but what we want is the one with the shortest or minimum weight. Okay, the path we want is the one with the minimum weight, and be very careful for the English word here. Okay, here I say a shortest path, right? A shortest path. It's not the shortest path. Okay, what does that mean? It means that shortest path may not be unique. Shortest path may not be unique. So what we are talking about here is any of such paths, as long as its weight is lowest, is minimum, then it will be said to be the shortest path, to be one of the shortest paths. Okay? So the shortest path weight from U to V is defined as, okay, the mean. Okay, so P is the path from U to V, and the WP, okay, the one with the lowest one, okay, is defined as delta UV. Okay. So delta UV, okay, will be defined to be infinite if there is no path from U to V. This is very natural, right? Because after all, we are trying to quantify the cost from U to V. If there's no path from U to V, which actually means no matter how much you pay, you would not be able to reach V from U, right? So that's why the weight, okay, the shortest path between U and V is defined to be infinite if there's no path between them. Okay? So with these definitions, okay, we also need to talk about this well-definedness of shortest path. If a graph G contains a negative weight cycle, then some shortest paths do not exist. If a graph G contains negative weight cycle, why? Think about this. If from U to V, you could possibly go through that negative cycle, okay, then you will not be able to define your shortest path, because every time you circle this loop, okay, the path weight is reduced, right? So you could pretty much create the path with the weight as low as possible. You know, and it could be it is pretty much unbounded, right? Say if you every time you go through the loop, the path weight reduced by 1, then you could go to negative infinite, right? So that is why in case like this, if a graph contains a negative weight cycle, some shortest path do not exist. But be very careful with the wording here. I'm talking about negative weight cycle. I'm not referring to any graph with negative weight h. You could have negative weight h, but it does not contain negative weight cycle, right? These are two different things. You could have negative weight ages, but you don't have any negative weight cycle. So if you have negative weight h, as long as you do not have negative weight cycle, the shortest path is still well defined. It's still well defined. But of course, in today's lecture, we are not going to cover that. We will cover that in the next lecture, which I think we will do that next week. I expect we finish these 3 lectures, hopefully, in 1.5. So maybe I will be able to talk about the Bellman-Ford today. Let's see what happens. So next one, a subpath, of a shortest path is a shortest path. So the shortest path has this optimal substructure, which is important for, it is important for both dynamic programming and greedy algorithm, right? In both dynamic programming and the greedy algorithm, we are looking for optimal substructure, And how do we prove that? Say this is the shortest path, So if from this node to this one, this is not the shortest one, let's say this node is U, this node is V, So assuming this shortest path, include this subpath from U to V, and we can prove by contradiction. If the subpath from U to V is not the shortest, if it is not the shortest, we have another path with the weight lower than this subpath from U to V. Then what we need to do is very simple. We just replace this subpath with this new shortest path from U to V, and the total weight from the source, from the first node to the last node, will reduce, right? Will be reduced. But this is obviously a contradiction to my original assumption. My original assumption is from this node to the end of the node, this is assumed to be the shortest path already. But now you are able to find another path with weight lower than that. So obviously we have a contradiction. So the only possible explanation will be our assumption is wrong. What is our assumption? Which is this subpath is not optimal, right? So this optimal substructure property exists in the shortest path problem. Okay, a shortest path. Okay, any subpath. Okay, not just from this node to this node. So any subpath in a shortest path must be the shortest path between those two nodes. Okay? So, with that in mind, okay, is the shortest path problem a dynamic programming or greedy algorithm? But before we answer that question, there's one more theorem that we should look at. Okay, it's called triangle inequality. Okay, for all u, v, x, so any three nodes, okay, we have the shortest path from u to v, okay, will be smaller than the shortest path from u to x plus the shortest path from x to v. Okay, this is not the triangle inequality that you have in mind in geometry class. It's different. It is different. But it is nevertheless very, very similar. Very, very similar. Okay, it's something like this. So I'm telling you, the shortest path from u to v, okay, the weight of this one will be smaller or equal to the weight from u to x, okay, the shortest path from u to x, and the weight plus the weight of the shortest path from x to v. Okay, there are two different scenarios that we can talk about. The first one is if x is a node in the shortest path from u to v, if x is somewhere here, then the shortest path from u to v, the weight of it would be the weight of shortest path from u to x plus the weight of shortest path from x to v, obviously, right? The equal sign, the equal will be, sign will be hold, right? Will hold, okay? If x is a part of the path. If it is not, it is impossible for this, the sum of these two weights, to be lower than the shortest path from u to v. Why? Because if it is, then this one would be the shortest path from u to v, not the one on the top, right? So again, this is a simple proof by contradiction. Okay? So let me repeat. There are two cases. If x is included in the path from u to v, then this inequality, the equal sign holds, obviously, right? Based on what we discussed in here. Okay. If it is not, then this weight of the sum of these two weights would be lower than this one. Okay. Why? We can prove by contradiction. If it is, then this one will be the shortest path instead of this one. Okay, so the proof is done. Okay. So this triangle inequality comes in very handy in our later discussion. Okay. So actually, okay, that substructure, optimal substructure, as I said, like once you see that, there are two possibilities. Okay, one is dynamic programming, one is the greedy algorithm. In this case, we are talking about greedy algorithm. But we need to first talk about the problem. Let's make the problem more, let's define the problem more carefully here. Okay, now you understand what shortest path is, and also some property about the shortest path, right? So the problem is like this. Assume, here is the simplified problem, okay? A simplified problem. A more general problem will be dealt with, okay, in the next lecture when we talk about Bellman-Ford algorithm, okay? So in this problem, we assume that all the weight, the weight for all the edges are greater or equal to 0. Okay? So this is a simplified scenario. Okay? In such a case, obviously, there's no negative weight cycle, right? Because every edge has, greater or equal than 0 weight. Okay? So all shortest path weights must exist because there's no negative weight cycle. So from a given source, vertex S, find the shortest path weights, okay, SV for all V, okay. So we call such a problem as single source shortest path. Okay, so you are given a source node. This source node is given. You are asked to find the shortest path from this particular source to all the other nodes. Okay, to all the other nodes. So this is the problem. Okay. So let's take a 10 minutes break. When we come back, let's continue the discussion about this problem. Okay?